being able to shift the pitch of a signal is a very fascinating application of what's called SSBAM, or single-sideband amplitude modulation. Just by way of a quick review, if you consider a baseband signal x of f, that is looking at it in the frequency domain, basic amplitude modulation would split the baseband signal into two halves, and each half would be then located at plus and minus the modulation frequency. The key idea there is that we end up with two replicas, one being shifted in one direction, the other shifted in the other. Single sideband AM, on the other hand, has the ability to actually shift the spectrum without actually generating the replica on the negative side. In order to see how this works, let's begin with an original baseband signal. I'll just give it the triangle shape because it's easy to draw. When we modulate that specifically by a cosine of frequency FC, FC standing for my carrier, we see the replicas shifted to either side, and also their amplitudes divide in half as well. If we were to modulate by specifically the sine function now, it's essentially the same idea, except we introduce essentially a phase shift. The j, which is defined as square root of -1, mathematicians would think of this as the imaginary value I, then that corresponds to a 90-degree phase shift. So as I say, it's basically the same idea, except we have some phase shifting going on compared to the cosine version. Now let me introduce the notion of a Hilbert transform. If we have a function h of t, which is defined as the Hilbert transform of some original signal x of t, mathematically this Hilbert transform is defined as the integral over all time for that original source signal x. We divide that by t minus tau, multiply the whole thing by 1 over pi. Seems kind of complicated, but it turns out that in the frequency domain, that applying this so-called Hilbert transform has the relatively simple effect of taking our original signal, say x of t, and multiplying it by either positive j or minus j, depending on which half of the frequency plane you're talking about. The so-called Signum function is very easy. It's just 1 for all frequencies greater than 0. It's 0 when the frequency is 0, and negative when the frequency is less than 0. So we can think of the Hilbert transform as a way of multiplying all of the frequency components of x of f by a phase shift term. Alright, so I'm kind of building this up in stages. If I have my original x of f, I then multiply it by minus j times -1. That gives me a positive j in the negative side of frequency. But then I have positive 1 for the Signum function on positive frequency, so that means that now the negative sign is no longer canceled. We have this picture for our Hilbert transformed x of f. Now if I take that previous result and modulate it specifically by the sine function, and at this point it's probably helpful to recall that the Fourier transform of a signal x being modulated specifically by the sine function has the following transform. That is, it's the original spectrum copied in 2, one replica shifted to minus f sub m, the other one shifted to plus f sub m, and then instead of dividing by 2, we actually use the scale factors j over 2 and minus j over 2. I'm going to go ahead and use the same carrier frequency throughout, so that's why I'm calling that FC down at the bottom. So if I take my signal and multiply one side by minus j over 2 and the other side by positive j over 2, and then we consider what happens when we're multiplying j's by j's. At this point, it's probably helpful to remember that j times itself is actually -1. So we have a net result of -1/2 and +1/2. And there is one more, just kind of reversing things to be able to draw things a little more effectively. Then we have the similar sort of behavior, except now we're multiplying by minus j over 2. And again, minus j times j is now +1. And we then have this new picture. Let me copy that same result. Let's negate this function, or negate this spectrum, excuse me. So I'm simply changing the sign of everything. Let's keep that. I've, again, kind of scrolled up my previous work. Now recall the original cosine modulated signal looks like this, and an amazing thing happens when we add these together. I'll show you how this works. Here we see that the values of 1/2 reinforce each other, and we end up with +1. Here we have -1/2 added to +1/2, cancels, goes to 0. Same kind of idea here. And what we find is that we have our original baseband spectrum basically pulled in half and shifted right and left. So we see that we can do a pitch shifting without actually introducing the sideband sitting on the negative side of things. And this becomes our foundation for allowing us to shift the pitch of a signal in a positive direction, or that is raising the pitch when the carrier frequency is 0 or greater than 0. And when the carrier is less than 0, then we can actually do a shift in the direction to get a lower pitch.